We will start over again. Welcome to tutorial 7 of tutorial 7 of analog electronic circuits. We are going to try to explore some circuits using inverter as an amplifier. So what we are going to try to build is a second order transfer function. And initially, for the concept building, we will use models of transconductor, which are as follows. We have this kind of transconductor. If we apply input Vi to the gate of this transconductor, the output current is in outside it. This is sourcing the current of Gm times Vi. And if let's say we apply the current at the input of the transconductor and it has a bubble at the output, that means it's sinking current of Gm times Vi. So we will initially use these kind of structures and later try to replace them with inverters as an amplifier. Let's begin. Can anyone tell what is a second order transfer function? How is the order of a transfer function decided? So the order of the transfer function is basically of the transfer function is basically equal to either the degree of the denominator or number of poles. So the denominator of a second order transfer function. So let's say we have the transfer function h of s is equal to n of s divided by d of s. So for now, let's assume n of s equal to 1 and d of s equal to, so the standard form to write the second order transfer function is s square upon omega naught square plus s upon omega naught q plus 1. So h of s can be written as 1 divided by s square upon omega naught square plus s upon omega naught q plus 1. Correct? So what exactly we need to make a second order transfer function. So let's try to put a circuit that can emulate this, that can build this transfer function. So let's say I have a voltage source which is Vi, and I have basically a capacitor, an inductor, and a resistor. Okay. So let's let the value of this inductor be L, the value of this resistor be R, and value of the capacitor be C. So the output of this circuit is taken at the output of the capacitor. So in this case, the impedance of your inductor will become S times L, the resistor will become be R, and the capacitor will be 1 upon SC. So if we do simple impedance division, so V out by V in can be written as 1 upon SC, that is the input, the impedance of the capacitor, divided by SL plus R plus 1 upon SC. This is clear to everyone, right? So if we further simplify it, it basically looks as S square LC plus SRC plus 1. So if we compare this with the original transfer function that we had, so we get omega naught as 1 upon root LC and 1 upon omega naught Q as equal to RC. So from here we can write the value of Q as Q is equal to 1 upon omega naught times R, and 1 upon omega naught, if we take from here, we get Q as equal to 1 by R times root C by, wait. So root LC comes over here, root L by C. So this is what we get. It's RC, sorry. So this is the quality factor. This is the omega naught. So this transfer function we have made using a voltage source. Let's try to build another kind of circuit that can give the same kind of same kind of transfer function. Let's try using a current source. So let's say this is I of S going into a parallel RLC network. So basically, can anyone tell what is the nature of this transfer function? Is it a high pass transfer function, low pass transfer function, or a band pass transfer function? So it's a low pass transfer function. So how is it a low pass transfer function? At h equal to 0, all of the S terms go to 0 and your response comes out to be 1. At h of S, when S is tending to infinity, all of your, so then your denominator goes to infinity and 1 by infinity goes to 0. So this is a low pass transfer function. Now, over here, we have what all quantities we have. First of all, we have the voltage that is developed at this node, that is V of S. Then we have IC of S, that is the current that is going into the capacitor. Then we have IR of S, the current that is going into the resistor. And we have IL of S, that is the current that is going into the inductor. So at very low frequency, we will try to explore like which of the V of S, IC of S, IR of S, or IL of S is going to behave as a low pass transfer function. So at very low frequency, at very low frequency, what happens with a capacitor and inductor? At so let's for now assume S as j omega. So at omega equal to 0, uh, what does a capacitor behaves as? So capacitor behaves as an open circuit and the inductor behaves as a short circuit. So what will be the value of V of S in that case at omega equal to 0? So the value of V of S at omega equal to 0 will be 0. Why? Because the inductor will be shorted, the V of S will be grounded. So what will be the value of IC of S? Again, it will be 0 because the capacitor is an open circuit at DC, so no current will flow through it. So IC of S is also equal to 0. What will be the value like where will all the current go in that case? So yeah, correct. So basically, inductor is the short circuit. So it's the it provides you with zero impedance. So all the current will flow into the inductor. So at very low frequencies, IL of S will be equal to IC of S. Sorry, I of S, and that basically gives IL of S by IC of S. That is the transfer function at from input to the inductor, from input current to the inductor current at S equal to 0 equal to 1. Okay, so at low frequency, it is satisfied that like only quantity that will be non-zero is the inductor current, that is L equal to that inductor current. So now what will happen at a very high frequency? The inductor will become, when omega tends to infinity, what will be, so inductor will become open. So if the inductor becomes open, in that case, what happens is IL of S goes to 0. So IL of S at low frequency is 1, IL of S at very high frequency is 0. So it turns out that the inductor current in this particular circuit is going to have a low pass transfer function. Again, we will try to write down the transfer function. So the transfer function will be R upon, so if we have, let's say, a current I going into three impedances, this is Z1, this is Z2, this is Z3. So let's say you want to find I's of Z3. In that case, I of Z3 will be equal to Z1, Z2 divided by Z1 plus Z2 plus, sorry, Z1, Z2 plus Z2, Z3 plus Z3, Z1. Or if you want to write it in terms of impedance, so let's say the impedance is Y1, Y2, Y3. That in that case, what you have is I of Z3 equal to 1 by Y3 is equal to Y3 divided by Y3 plus Y2 plus Y1. So using this formula, if we try to find out the transfer function of from input current to the inductor current, our transfer function will look like IL of S divided by I of S is equal to, so this is basically this fraction times I. So IL of S by I of S is equal to the inductor impedance, sorry, inductor admittance or conductance. So can anyone tell me what is the inductor conductance? Conductance of the inductor YL. YL is equal to 1 by SL, and YR is equal to 1 over R. Let's call it G, and YC is equal to SC. Okay, so if we write down the transfer function, we have 1 over SL divided by SC plus G plus 1 over SL. That gives us the final transfer function as S square LC plus S times G times L plus 1. So now again we will compare it with the standard second order transfer function. So standard second order transfer function looks as follows: S square by omega naught square plus S upon omega naught Q plus 1. So omega naught is again 1 upon root LC, and 1 upon omega naught Q is equal to L times G. That implies 1 by G L omega naught is equal to Q. So if we substitute the value of omega naught into here, so we get quality factor as 1 upon G times root. So we have root LC over here, root C by L. Is this clear to you? Is there any doubt till here? So to summarize, we have a current source that pumps current into a parallel RLC network. So this case, we are calling it representing resistor by its admittance, that is G, and capacitance C, and then and inductance of value L. And if we try to find out the current that is going in the inductor, if we have I over here, IL over here, so IL of S by I of S basically gives us a low pass transfer function as a square upon omega naught square plus S upon omega naught cube plus 1, where our omega naught is equal to 1 upon root LC and our Q is equal to 1 upon G times root C by L. Now, let's say we want to implement this low pass transfer function in integrated circuit. That is NIC. So in integrated circuit, making inductances is a very costly affair because inductances are very bulky, and even if you try to make it on integrated circuits, they won't be very good in inductance. They will have some series resistance in pair. They will have a lot of series resistance in parallel to them, and their quality factor, the standalone quality factor of these inductances won't be very high, and they will behave as an inductance for a very small range of frequencies. So building wide-band circuits, you generally tend to avoid inductances, and especially at very low frequency, the value of inductance required will become so huge that it is not feasible on integrated circuit. Typically, we can build inductance in terms of a few nanohenries on the IC, but not more than that. So what we do is, let's try to get a circuit. So basically what we want is, we can build a resistance of value 1 by G easily on the integrated circuit. We can build a capacitance of value C easily on the integrated circuit. And we can, so this current source, we can use it, we can use, let's say, we can use a transconductor of a value G with an input of Vi over here. Okay, so this will give you GM. Okay, let's call it G only. So G times Vi current it will give. Only missing piece of puzzle is basically an inductor, and we need to tap its current. Okay, so we can't build inductor, of course, on the circuit, but it's very easy to build a capacitance on a circuit. So basically what we want is looking in admittance from this node to be of S by L, the Y that, so basically if you, what kind of circuit we want is, if you place, if you put a voltage of V on this node, the current that this particular black box, so this is basically, we are trying to emulate an inductor on the IC. Let's call it emulated inductor. So the current, if we put a voltage of value V, the current that they should sink in needs to be of the value SL times V. Okay. So this is the requirement that needs to be fulfilled. So initially, while starting the lecture, I told there are two kinds of transconductors that can be built. One is basically this thing, where you give input and a current is sourced with value of G times Vi. And then there is another kind of transconductor, the complementary one. Yeah, bubble one, correct. So Vi, this can sink a current of G times Vi. So in this case, so let's say if we have a voltage of voltage with V with value V, and we use, let's say, a bubbled current. Okay, and let's say this has some transconductance called G1. So if at the input of this, so what input must be applied at this particular node, at the input of the transconductance, so that a current of SL times V can be synced from this particular, can be synced by this transconductor. What should be this V of I? So we can do the math. It's a simple math. SL times V should be equal to G1 times Vi. That means the input voltage that this particular transconductor needs to have is SL by V times G1. Okay. Is this clear to you? Okay. So now we need, now another task for us is to generate this voltage, that is SL times V divided by G1. Okay. So in order to generate this voltage, what basically we are going to do is, so basically this, how this voltage can be generated now. So let's say, so basically there is a voltage V. If let's say some current, so basically there is some current I that goes into a capacitor. What kind of and this capacitance has a value of C. Okay, so what is the voltage that is developed at this node? I by uh, just a minute. The voltage developed is, wait a second, it's SL. Oh, just a minute. So here I had a little bit of mistake over here. So the current that needed to be synced won't be SL times V. It will be V divided by SL. So basically, 1 by SL is the admittance of an inductor. So V divided by SL current we need. So basically, this has to be V by SL. So the input voltage has to be V upon SL times G1. Now, in this case, the voltage we claimed that it will be I divided by SC. So we can see that this voltage and this voltage are of similar form. So what we need to do is, I will copy the circuit from here. So if let's say we had a capacitance over here with a value of Ci, and we were able to push in a current into this particular node, then this node will have a voltage of Vi of the form I divided by SC, sorry, I divided by SC, which is the exact same form of voltage we need to put on this node. Now, we want that, now in this case, we see that we need the voltage to be directly proportional to the input voltage, that is V, that we are applying at this node. So that means to say, if I is in proportional to the input voltage, then we can get this form of voltage at this node. Do you understand? So, what can we use in order to generate a current that is basically proportional to the voltage V? So again, we can use a transconductor. So we need this kind of arrangement. So let's call the value of this transconductance as G2. So now, there can't be no current can flow in this case because transconductors is basically a voltage controlled current source, and the property of a voltage controlled current source is that it has infinite input impedance. So no current, so current that will be flowing in this case will be zero. So the only current that will be taken by this complete block will be the current that is synced by this G1. Now let's try to calculate what is the voltage at this node. Vi is equal to I, the current divided by S times the capacitance. So the current is V times G2 divided by SCI. Okay. And then this current that is synced by this this particular the bubbled transconductance will be this times this G1. So the V by SL that we needed is equal to V G2 G1 divided by SC1. Okay, is this thing clear to you guys? Okay, so let's just quickly see whether this is dimensionally correct. So we have SC1. So this will be a dimensionless quantity, SC1 by G. This will be in radian per second. And this is basically admittance, and this is also admittance. So yeah, this is a dimensionally correct formula. Okay, so that goes to say that this particular block, I'll mark it in red. This particular block will emulate an inductor with a value L is equal to C1 divided by G2 times G1. Is this clear? Okay. So for now, let's take G1 equal to G2 equal to G, and this value C1 is equal to C. So let's go back to the original circuit. So this was the original circuit that we were trying to emulate. So we can easily get a conductance, we can easily get a capacitance, and now we have seen how to get a inductance using a capacitance and a few transconductors. So we will put the complete circuit into place. So for the current source, we have 1G over here. Input we provide over here. There's a resistance with value 1 by G. Then we have a capacitance over here. And this is basically emulated as follows. G1, G2. Okay. So Basically, this is the current that is going into inductor, okay? And if this is the current that is going into inductor, this current divided by if this is the current, let's say IL, and this voltage at this node will be, what will be the voltage at this particular node? This will be, okay, if this voltage is, let's say, so basically, yeah, IL upon G2, negative of IL upon G2. Oh no, sorry, IL upon G2, correct. So this is IL upon G2. So initially we saw that the inductor current is a low pass filter. So now this particular voltage is proportional to the inductor current with just a scaling factor of G2. So that means to say that this voltage will also be a low pass transfer. This voltage will also have a low pass transfer function. Is this clear? Okay. Now let's try to find out let if we are emulating everything with using a transconductor. Let's try to see whether we can emulate this resistor as well using a transconductor. So this is just a grounded resistor. So what we can do over here is, so basically, how does a resistor work? If you have a voltage V, so and this is a resistance of value 1 by G. So what is the current that will that this resistance will take in? This resistance will take in the current of V by R, that is equal to G times V. Okay. So if we want this to take, if we want this to sink G times V of current, that means to say, if we had a voltage V over here and we used a bubbled transconductor with the voltage V over here as well, so this could have sunk in G times V current. Do you understand? Okay, so like we want V voltage over here. How we can get V voltage over here? So what if we directly short this over here? Will this work? Okay, correct. Because see, can there be any current that can flow in this direction? So, why? Because the gate of there can't be any current that can flow in this direction, because yeah, the input impedance is infinity. So, current will only flow in this direction, and this voltage and this voltage is equal. That is equal to V. So, the current, overall current that this complete contraption will be sinking will be G times V, which is equal to standalone resistor. So basically, this can be emulated as follows. So we have G over here, we have input voltage over here. So this is a bubbled transistor. Then we have a capacitor over here. Then we have G1 over here. We have G2 over here. This is G. And we have C over here. So this is, and if we take the output over here, so this from input to output, we know that it will be a small low pass transfer function, second order low pass transfer function. Is this clear to you guys? Okay. So now let's try to find out finally the transfer function from the input to output. So the current that will be flowing from this is basically G times Vi, and the overall voltage that will be developed. So we need to find out the current that this will sink a current of V naught by G2. Okay. So if we try to put KCL at this particular node, so basically what we have, let's say the voltage is at this node is suppose V1 and this is V naught. So V1 times G, oh sorry, yeah, G2 times V naught over here. So V1 times, so KCL at node 1 is basically V1 times G plus V1 times SC. So this is the current that is being synced plus V naught times G2 is equal to G times Vi. Is this correct? So basically this is equal to V1 times G plus SC plus V naught times G2 is equal to G times Vi. Now we will apply KCL at output node. So KCL at output node. So this is the current that is flowing into this node. What will be the value of this current? So we assumed the voltage at this node to be V1. So that will be G2 times G1 times V1. This particular transistor has G1 voltage, transconductor has G1 voltage, and at the input it has V1 input. So basically the KCL at so the current that will be being pumped into this node is G1 times V1. That is basically equal to the current that will be pulled by this capacitor. No current will go in this direction because this is an infinite input impedance. So this will be equal to V naught times SC. We have equation 1 over here, equation 2 over here. So basically from here we can say that V1 is equal to V naught times SC divided by G1. So from here this can be substituted in equation 1. So in equation 1 we have V naught times SC by G1 times G plus SC plus V naught times G2 is equal to G times Vi. So what we have over here now, we will take V naught common. So we will have S square C square divided by G1 plus G2 plus, sorry, SC G by G1 plus G2 is equal to G times Vi. So V naught by Vi will be equal to G divided by S squared C squared by G1 plus SCG by G1 plus G2. So G2 we can take out as common. So in that case, G by G2 divided by S square C square by G1 G2 plus SCG upon G1 G2 plus 1. So this is basically the final thing that we get. Now, uh, wait a second, is this correct? Square C bar by G1 G2 SCG divided by G1 G2. Now the gain, so if the gain that was there in the original transfer function, we want the same gain over here. That means G should be equal to G2. Now G is equal to G2, so our omega naught is basically equal to so our omega naught is basically equal to G is equal to G2, the numerator becomes 1. Our omega naught is basically 1 upon omega naught square. So this is if we compare the term of second order, if we compare the coefficient of second order term, so 1 upon omega naught square. I'll write the standard transfer function here for reference. We'll compare it by 1 upon S square by omega naught square plus SCG upon G1 G2 plus 1. Okay, so comparing this, what is omega naught? It is square root of G1 G2 divided by C squared, and G1 is equal to G, so this, and what is 1 upon omega naught Q? That is equal to C. G and G2 can be cut because they are equal. G by G1. Wait a second. S upon omega naught Q. So from here, Q is equal to 1 upon omega naught C times G1. So we can substitute the value of C from here. So we get substitute the value of omega naught. So it's basically C squared by root of C squared G1 times G. And this is basically G1 at the top and C at the bottom. So C squared, square root of C squared and C can be cancelled out. So the omega naught we get as square root of G1 by G. Okay. So here we saw that how this second order transfer function can be emulated using only capacitors and transconductors. So now only capacitors and transconductors are used in the circuit. So this is called a GMC biquad. Why it is called so? So GMC biquad, GM stands for the transconductor. So there are only transconductor and capacitor. So GMC and biquad because it implements a second order transfer function. So and the low pass transfer function we get at the output of V naught. Okay. Now Till now, we have used models of these transconductors that are of value G. So in that case, we can replace it by the actual inverters and see how it happens. So basically, the primary condition for an inverter to work as amplifier, what is the primary condition for that? So let's say I have an inverter over here. So both P and N have to be in saturation. So one way for both P and N to remain in saturation is basically if you connect. So this I think you have learned in class that if you connect input and output of a inverter, in that case, basically, or in other words, if you somehow are able to make both the input and output, both input, the DC value, the operating point of both, I will write it in capital, VI and V out equal to the biasing voltage of a transconductor. That's called the self-bias voltage. You guys have learned about self-bias voltage, right? Okay, so we will discuss that in brief. So basically, this is the structure of a inverter, a CMOS inverter. And what we are going to do is, if let's say we short this particular the input and output, so both of them come and bias at one particular node. Now, in this case, both for drain, if the current is like if there is any current that is supposed to be flowing from this particular path, so can any of the transistors be out of saturation? Let's assume a current is flowing. So in that case, can any of the transistors be out of saturation? What is the condition for a transistor? For example, let's consider NMOS. What is the condition for this transistor to be in saturation? Can anyone tell this? So basically, your gate voltage should be, your drain voltage should be at least greater than or equal to one threshold below your gate voltage. Okay. And for PMOS, what is it? Your drain voltage shall be less than or equal to modulus of one threshold below. So the threshold voltage is basically, yeah. So you can write it as VG plus VTP, or you can write it as VG minus modulus of VTP. So yeah, both the way you can write. VTP is a negative quantity. So yeah. So these two conditions need to be met for both the transistors to be in saturation. Now, can you tell, now can you see that this condition be violated if both the input and output are connected to each other? So this is the gate voltage VGD 0, correct. So if VGD 0, that means to say that both the gate and drain are equal to each other. So neither for the PMOS this condition is going to be violated, nor for the NMOS this condition is going to be violated. So that means to say that both NMOS and PMOS are going to be in saturation no matter what. Now, if the current is flowing like this, let's call this current ID or let's call the current of the inverter. Will there be any current that will be going in this direction? No, correct. Because the input impedance of both the gates of PMOS and NMOS is infinity. So there won't be any current that will be flowing in this direction. So whatever current NMOS will be flowing through PMOS will be equal to the current that will be flowing through NMOS. Okay, so IP is equal to IN. Now, what is the value of IP? Value of IP is half mu P Cox W by L times P times, this is some VDD, this is some V naught. Okay. So times V source gate minus modulus of VT whole square. Okay. And V source gate is basically, as you pointed out, VDD minus V naught. So we have IP is equal to half mu P Cox W by L times P times VDD minus V naught times modulus of VTP whole squared. And similarly, what is IN? That is equal to half mu n Cox W by L of n, that times V naught minus VTN whole squared. Okay, so and since these two transistors are in series, so the current that will be flowing from input to from PMOS to NMOS will be same. So in this case, what will happen is IP is equal to IN. Okay, so if we equate equation 1 and equation 2, in that case, what we get is we can directly equate it, and we get VDD minus V naught minus modulus of VTP whole squared divided by V naught minus VTN whole squared is equal to, so Cox will be equal for both, and so this will be mu P W by L of P divided by mu N W by L of N. So now taking the square root, we have VDD minus V naught minus VTP divided by V naught minus VTN is equal to square root of, let's call this Kp and let's call this Kn. So Kp by Kn. So we have VDD minus V naught minus VTP is equal to square root of Kp by Kn times V naught minus VTN. Okay. And yeah, if again, if you call as root Kp by Kn as R, so in that case, VDD minus VTP is equal to V naught times 1 plus R minus VTN times R. So basically, V naught is equal to 1 divided by 1 plus R times VDD minus VTP plus VTN times R. So this is the self-bias voltage that we get. So uh, at this particular voltage, when input and output both have this particular voltage, your both PMOS and NMOS will be in saturation, and that can behave as an amplifier in that case. So what we need to maintain is, now let's come back to our original problem, that we wanted to make this circuit using inverters and capacitors. So what we need to maintain in this case is, let's copy the circuit. So, let's say an inverter over here, if somehow I'm able to make both input and output operating point voltages equal to the biasing voltage, this particular inverter is going to behave as a amplifier. So if that is the case, how will it behave? So let's say, let's consider this for now. So I give uh, So this is the small signal input. This is basically equal to the self-biasing voltage. I have VDD over here, I have ground over here, and over here, let's say I somehow give using an inductor, let's say somehow give the self-bias voltage over here, and I take the output over here using a capacitor. So in this case, at DC, of course, and let's say this inductor goes to infinity, this capacitance goes to infinity. These are very large value. So this inductor is just for representational purpose. We will remove it as we progress in the circuit. So in that case, basically this particular inverter will behave as an amplifier, and what will be as an amplifier or as a transconductor. So let's say since we want it to behave as a transconductor, so let's just directly put a voltage source of VB over here. So if this is GMN, and the transconductance of transistor NMOS is GMN, the transconductance of PMOS is GMP. So the small signal voltage, the small signal input voltage is VI. In that case, what will be the current that will be going inside this voltage source VB? It will be so there is no capacitor over here for now. I'm just talking, and let's assume the RON and ROP are infinity for time being. So the current that will be going over here is, there won't be any current going inside VP. There will be current that will be sinking. So there will be a part of current that will be sinking into the PMOS. And mind you, I'm talking about the small signal current. There will be some quiescent current that will be flowing that we calculated just now based on the self-biasing condition of the inverter. And on top of that, when incremental current voltage is applied as VI, a small signal current will be synced in, that will be GMN times VI into the NMOS, and there will be some current that will be synced in, that is GMP times VI into the PMOS. So overall current that will be synced from this voltage source will be GMN plus GMP times VI. Negative. So the current that will be sourced will be minus GMN plus GMP times VI, or the current that will be synced will be plus GMN plus GMP times VI. So basically, an inverter, if somehow we are able to manage to bias both input and output at the biasing voltage, this will behave as a bubbled transconductor that we discussed initially. Do you guys agree? Okay. So now let's try to build this circuit using that. So first of all, this particular, let's try to focus on this particular stuff. So this we basically we need a bubble transconductor which whose input and output are shorted. So this is just straightforward, right? If you short basically the input and output of an inverter also, it is same as basically shorting the input and output of a transconductor. And here, if let's say there is some input voltage VB flowing into this particular thing, then this will behave as a transconductor of value GMN plus GMP. And this will be biased at voltage VB. Is this clear? Okay. So now we know that. So this part of the puzzle is complete. So we have this over here. So this basically behaves as our conductance or resistance, and the voltage, the quiescent voltage at the input and output of this transconductor is equal to VB. Okay. Now let's worry about the input transistor or the input inverter. So if we connect it over here and input we give as fixed voltage VB plus incremental voltage VI. In that case, the this inverter also is basically biased at this inverter also is biased at VB, correct? Both input and output are biased at VB. Is this clear? Okay. So this basically behaves again. This behaves as the input transconductor that we had. Now the capacitance is just passive capacitance that is okay. Now again, I will take this circuit down. Okay. So this particular now this G2 G2 over here can be basically made as this thing. So this is a bubble transistor, bubble transconductor. So its output is now biased at VB due to the biasing of this conductance. So output is certainly biased at VB, and here is this capacitance over here. And now only thing that we need to fill is the upper transconductor. Is this clear? Okay. Now upper transconductor is a positive, so it needs to source the current. It does not needs to sink the current. So we need to somehow make this particular block as a sourcing current. So two inverters cascade. Now the problem with two inverters cascade, a simple two inverters cascade will be that basically the gain of these two will get multiplied. Okay. So let's say we had, let's assume that this is biased at whatever biasing it needs to be. If this has uh, a transconductance of GMN plus GMP, and this has a transconductance of GMN plus GMP, and let's say there is infinite there is infinite output resistance of the inverter. So in that case voltage from here to here will go to infinity, right? Because the current has nowhere to go. So if the finite current goes into infinite impedance, the voltage at that node becomes infinite, correct? Yeah, and if the voltage at this node is infinite, then the current at the output of this second inverter will be infinite. Okay, so this does not serve our purpose. We want a finite transconductance from this particular thing. Now, let's try to see how we can achieve that. So, there are two problems over here. So, assume that this is biased at VB and its output is biased at VB. Let's say both these things are taken care of. Just a minute. Mm, okay. And this output is biased at VB. So both of these things are taken care of. Now, the only thing that needs to be done is first of all, you need a finite gain from here to here. Ideally, you want a gain of unity, and you also need to bias this particular node at the biasing voltage of VB. Correct? Yeah. So, initially at this node, how did we try to bias this voltage at VB? By putting inverter in this configuration, correct? Yeah. So this is self-biased and the voltage at this node is biased at VB. So that problem is taken care of. Now, can you tell me what is the gain from input to the output of first transistor? Correct, it's one. Why it is one? Because the transconductance, the current that this thing will be pumping, it's not one actually, it's minus one. So the current that this thing will be pumping will be or sinking will be minus GMN plus GMP. This current will be synced in by this inverter, and if this and this basically will behave as an impedance of 1 by GMN plus GMP. So basically current into impedance will give you the voltage at that node, and these two will be cancelled. So the gain from input to out this node will be minus 1. Okay. Now if now what we have over here is VB over here, this thing over here, and a VB over here. So now this voltage is biased at VB. The gain from here to here is minus 1. And the gain now, if this is VB plus some small signal voltage as VI. So so if this is VI, what will be this voltage? The incremental voltage at this node? It will be minus Vi. And what will be the current that will be sinking or being, so now will this inverter sink current or source current? This will source current, correct? So this will source current of Vi times GMN plus GMP. Okay. So this complete block over here will behave as a positive unbubbled one, correct? So this can be just plugged in over there. So our final circuit is this capacitance over here. this capacitance. Now this transistor, now this complete configuration can be, so basically, let's say this is GMN plus GMP. Now, if you want a, different value of transconductance from this, so you can suppose, let's say, like put two of these things in parallel, you will get 2 GMN plus GMP. Or if let's say you reduce its size by half, you will get a half GMN plus GMP. So by scaling these inverters properly, you can achieve the transfer function you need. And this will basically behave as your second order transfer function made completely by inverters and capacitors. Is this clear to you? Okay. Any other doubt? And I think this is one of the questions that is there in this week's assignment. So now you can appreciate how that particular question, like that particular circuit that has been put in that assignment, comes up. So yeah, this is the inverter chain question, and like this is basically the rationale behind the circuit that is present in that that is there in that particular question. So now, if let's say there is this has a non-zero output impedance, so even if it has a non-zero output impedance, the that non-zero output impedance will come in parallel to the 1 by transconductance of this inverter, and which will be a very small quantity, so that can be ignored. And similarly, so yeah, like if there is a non or if you want to find out the exact transfer function, you can do it as well. But like in this particular tutorial, I wanted to just explain how that particular circuit comes by. Any doubt in this or any other thing? Okay, so if there is no other doubt, so like that's all I had to say for this tutorial. Thank you for attending.